This tutorial is about creating a RAPT run, designing from scratch. So we're going to start with what we have is a layout for a car park. We can assume that that's given to us, or the column locations are given from an architect or a planner. And we have to come up with a slab arrangement that's going to work for this column arrangement. So our options are a flat plate, a flat slab, or a band beam system. I'm going to go with a band beam system because the spans in one direction are a little bit longer than the spans in the other direction. So 10 meters versus 8 meters. And a banded system can be very efficient if we can get the design to work such that we don't really have any bottom reinforcement. That way we only have, or we have a logical sequence of construction where we'd have PT laid and then top reinforcement laid. Okay, so to start, we need to estimate what we think the band depths, widths, and slab depths will be. And for a band beam, and if you want to know what span to depth ratios you should use for various loads and for various spans, just have a look for any PT guidance on the web. A good one is one by Ed Cross. So we go with our beams. 27 span to depth ratio is appropriate for band beams, internal bands. And so we take our largest span, which is 10 meters, and we divide that by 27, and we find that a rough estimate for the depth is 375 millimeters. Now we can look at the slabs. Well, actually, before we do the slabs, let's do the width of the beams. So the width of the beam should be roughly 0.2 times the span of the slab. So 0.2 times 8200 is going to give us roughly 1640. But obviously we always want to work in increments of 300 because that's what the plywood widths come in. So we will go with 1500 wide. So we have 1500 by 375 deep band beams, and our slab depths will be based again on slab to depth, span to depth ratios. Internal slabs will be 52. So we do 8200 divided by 52. We get 160, and end spans should be a span to depth ratio of 46, which will give us a slab depth of 180. So let's mark this. Let's mark this up so that we have a feel for what we're designing in RAPT. So we'll put in the beams. So 160 internal slab panels, 180 end span slab thickness, and then a 375 by 1500 wide deep beam. Okay, let's open a new RAPT file. So I've got RAPT open already. We go File, New Frame, and we want to, well, let's start with the design of the main beam. So we've got 3 spans and 2 cantilevers. So that'll be 3 spans, a left cantilever and a right cantilever. We're going to design the internal panel. For simplicity, we're going to design this center panel here, which is 160 on both sides. But if you wanted to design this one here, you would just take the average of the 2 slabs at 170. We change the office type to parking. Now that affects your load combination factors, but it really only affects it for Eurocode. So for AS3600 and ACI, that won't change much. Our loading type we change to vehicular pedestrian, and that changes the deflection limits that RAPT will apply. The parameters that are set by choosing these things can always be changed once we go into the run. So this is not your last chance to change those things. Now we're choosing the structural system, And the same thing as before, whatever we choose here, we can change down the track, so you're not locked into anything. So we want a one-way, it's a one-way beam with a slab, and we're going to start with the beam, and then we're going to go back and do the slab. So we'll do a one-way beam and slab. Our span length will start with 10-100, cantilever length 3400, our slab depth, as I said before, 160, and our slab panel width a 200. Let's say our columns are 3 meters up and down, width 200, 800 long. Our beams are 375 by 1500, and let's keep them rectangular for now. Our initial dead load will be 0.5, extra dead load will keep as 0, just noting that the difference between those two, initial and extra, is that extra dead load affects your incremental deflection. So in other words, your brittle finishes will be subject to the deflection, which would include this extra dead load. Your brittle finishes wouldn't be subject to deflection under initial dead load because it's applied before the brittle finishes are put on. A live load 2.5 kPa according to the code AS3600, and if you're using a different code, then you just put in your appropriate live load. And we do want a pre-stress frame, so we click yes there. It's asking us for what pre-stressing ends we want. Now the total length of this system is roughly 30 meters, so that would be the limit of a single stressed end. We wouldn't really do a double stressed PT tendon here, only because you don't need to. So we will leave it on the left, and the number of, or the fraction of self-weight we want to balance our, the fraction of self-weight we're going to balance with PT will be about 0.8. And there are various rules of thumb for what the most efficient and economic percentage of load balancing you should do for various live loads and various types of structures. For car parks, 0.8 is about right. So we'll click OK, and then RAPT will set up the run for us, and we'll have to change only a few things to get this working. So let's start here with our concrete. Concrete is 32 MPa. We will choose 40 MPa just because we want to have quicker cycle times, and it improves our compressive stress limits and our tensile stress limits for the members under PT. We're going to spans and adjust our middle span here, which should be 6,800. Everything else looks right there. Our columns, these all look right except for one thing, which is our stiffness. So our stiffness is currently set at 100%, and we should really drop that down to a number which ensures that the moments in the beam and the slabs are maximized, so we're conservative. So we'll drop this down to a level which is artificially low. That will reduce our deflections. It will slightly overstate our deflections, but we can always come back and change that if we're right on the limit. Okay, going to our beams, we have the beams as we set them up at the beginning. They're all fine. We don't have any drop panels. We don't have any transverse beams. We don't need to add any elements or layers. But again, if you wanted to create a thicker element on one side, this is where you would do it. You could add a thickening on one side. However, as I said before, the easiest thing to do is just take an average of the two slabs either side of the beam. We have no steps, so it's just our load cases and load combinations. These are already set, so self-weight is determined by RAPT. Your initial dead load was set at the beginning, your live load at 2.5 kPa. Our combinations are all predetermined, similarly for deflection. And so now we can go to pre-stress, and this is what RAPT has added to ensure we balance our loads at 0.8 0.8 of self-weight. So it's given us 4.22 tendons, which is not obviously a real number, and we have to put in a whole number here to make that logical. So let's start by rounding that down to 4. Okay, we need to set our covers now, our minimum cover. That'll be determined by your fire requirements and also rules of thumb for PT, which is that on the bottom, your minimum cover should be about 25 millimeters so that you don't have any popping of the tendons. Similarly, on the top, we would normally have a minimum of 20. However, we know that in the opposite or the orthogonal direction for the slab, we don't want to clash. And so the slab will run over the top of the beam PT, and so we will ensure that the PT for the beam is set down 40 millimeters cover, and the slab will be 20 so that we don't have a clash at the high points of the columns. So we have our various profiles, and we can change those. You know, we can put in a straight section here if we wanted to. We don't, so we'll leave them as is. We go to our allowable profiles, and this is just the parameters that dictate what profiles we can put in when we put in the profile we want. So and this sort of helps RAPT, gives RAPT parameters around which it should set the profiles. So again, we've got 40 millimeters from the top. Now from the bottom, this is the number we're putting in here is our tendon cover, and as we said before, our tendon cover minimum of 25. So this is all correct, and we can now go to the profile that we are adopting, which is what you can see printed out on the screen here in the graphic. So when we look at the low points, we are not really taking advantage of the full section depth. So let's drop the profile depths here and here, and that will give us a much more efficient system. So we go here. Now this number here, 139.8, the reason that's different to the number here is that this number is the distance to the underside of the duct, so the cover, and this number here is the distance to the centroid of the strand. So this is our access distance essentially. Now your access distance is often dictated, or the minimum access distance from the surface, any surface, is governed by fire. For this particular design, we are going to assume a 120-minute FRL, or 120-minute fire limit, and for that we will need a minimum access distance of 35 millimeters. Sorry, I beg your pardon, a minimum access distance of 30 millimeters. That's to AS 3600, and then on top of that, AS 3600 requires another 15 millimeters for PT. So that number here is going to be 45 millimeters, and this number here, 45 millimeters as well. We will leave this one here because we're obviously not going to need as much capacity right in the center. So let's look at our output to start with, and we can look at our strength and our deflections just to give us a feel for whether or not this is in the right ballpark. So let's start with our deflections. Okay, so our deflections are not bad, but we are certainly popping up slightly too high in the middle. RAPT is saying that we have a little bit of a problem with our bottom axis, a bottom axis distance, so we'll have a look at that in a second. Let's also have a look at our ultimate capacity, and you can see that this design is well and truly in excess of the design moments and the minimum moments. So if I click here and I look at the initial capacity versus, say, our minimum design or our ultimate design moment, we're twice 3 times what we need. So we have too much PT in there. And in fact, if we look at our P on A, we go to text and go to service and look at our P on A. Our P on A is not terrible, could be slightly high, but it's acceptable. But we certainly are over designed from a strength point of view. So we could probably reduce the section depth. So let's go back to spans and beams, and we will drop this back to 350. I'll update my sketch. And go back to our pre-stress. We can look at the errors here. We talked about drapes before, so we look at this one here. No errors in the profile, so we're okay after that change. Now let's go back to our output and let's have a look at our capacity. Okay, again, we're still well in excess of the capacity required, and we could probably take some PT out of this. So we've probably got too much post-tensioning. Let's go to our post-tensioning and let's drop our number of post-tension strands to an anchorage of 4 and 4 strands. Okay, when we look at that, that's getting a bit closer. So you can see here where in fact, RAPT is adding a little bit of reinforcement on the one end. So you can see here, RAPT is adding reinforcement here. And the reason that RAPT is adding reinforcement there, we can find out by clicking I. And here we can see that RAPT is adding reinforcement for serviceability, in other words, crack control. And the reason it's doing that is because if we look at our service graph, we have a limit on the stress, which is 0.25 times the square root of the characteristic strength of the concrete. That's that dotted grey line, and we are exceeding that here. And so RAPT is adding reinforcement to try and bring that down. Now, why isn't it doing it on the other side? So it's adding it here, but not here. The reason for that is that there are pre-stress losses causing that the pre-stress to be on this side to be less effective than on this side. We could improve that by adding two live ends at this end and 2 live ends at this end. So we're effectively got the best of both worlds. So let's do that. We'll add in a right-hand stressed tendon. It'll also be 4, but we only need 2 on. We had 4 before, so we now have 2 and 2, both equal and opposite, if you like. Just got to make sure with this one that we've just added that we ensure that the drapes are the same. So let's change that. Our axis distance on the bottom was 45 millimeters from memory. And, oh, look at this. It's we've got a 35 here. We need to make that 25. That's why it's causing a problem. So we can now change this to 45, and we're getting very close to matching now. Our cover to the top, 40. And if we look at our other tendons, okay, so in the first one that we had a top axis distance here of 297.8. This is the same here. And it looks like actually in this first one, we need to fix this one up here to be 297.8 as well. Okay, our center line, 95. This should be 95 as well. go back to our first one here. 205, 200.4, let's make that the same. And finally, got 205, 205, 205. Doesn't like that for some reason. Now we are very close. We just want to bring up this end here. We want to bring that up to the same number that this one was, so 120. So this one, 131.8. We'll take that up to 131.8 as well. And now they are very close. So let's look at what that's done. We'll go to output. And you can see now that RAPT doesn't need to add any reinforcement at this end for serviceability. Our ultimate strengths are all fine. We'll have a look and confirm that looking at the reinforcement layout. This will tell us if RAPT wants to add any reinforcement. And you can see that RAPT hasn't shown any reinforcement required there. So we've just got our PT showing. Sorry, we've just got our PT in this design at this stage. We can go through the various checks that it's done. It's checking that our capacity meets the minimum strength and the design moment, which it does. Our neutral axis depth needs to be below a limit that ensures that we are ductile, that is 0.4, and that can be lower if we want to redistribute moments, but we are not requiring that in this design. Our final design condition is the same as the initial design condition because RAPT hasn't added any RIO, so there is no change there. Its service checks, it's looked at compressive stresses in the section at at service. It's checking cracking, ensure we don't have too much stress in the bars. It is then doing checks on transfer pre-stress, so ensuring that our compressive stress limits aren't exceeded, and that if there is any cracking in the section, that reinforcement is added if it's needed. Okay, so then again we can go to shear design. In shear design, for AS3600 in particular, KS5VUC, which is this column here, is the limit at which reinforcing or shear ties are required. So at all stages you can see that this number here is bigger than this number, and so we do not need any shear ties, which is why RAPT has not given you any suggestions for spacing and number of legs. Spacing of these various options. Punching shear is shown to be okay, but we'll do that again when we look at the slab design. Finally, we look at our deflections. In our deflections, not terrible, but again, we have this middle section popping up and we don't need that to happen. So we can move the PT drape in this section and shift it up, which will drop this point here, but it'll also reduce our ultimate capacity in this zone because we're shifting the reinforcing toward the compressive zone. So we want to have a feel for how much we can shift it. So we look at our our bending moment diagram. We can see under sagging we have quite a bit of play to shift that tendon up, and so we will shift that up. Now it would be a trial and error to shift this up to see at which point it works, but I have already done this and I know that 260 is about the right number. So 270, and change this one to 270, and we should find that that gives us a fairly good deflection profile. It hasn't affected our strength, so you can see that our initial strength is just higher than our minimum strength, which is 133. And if we look at our deflections, we're a little bit better. So we've sort of brought this down and popped these larger spans up to 11.6 millimeters. Okay, that is our beam done for now. Now let's look at our slab run. So we will create a new run. So we open our dialog box, new frame. We have now 1, 2, 3, 4 spans. It is a pre-stressed frame. We add the same details as we had before: parking, vehicular pedestrian loads, and now instead of a one-way beam and slab, we have a one-way slab and beam, which is essentially just the orthogonal direction. We're now designing the slab. Our span length is 8200. Our slab depth is 160, and we'll add the end span depths later. Our panel width is going to be the average of 10.1 and 6.8 meters. That's 8,450. And our slab design width, we're going to use 1500. And this slab design width means the width across which RAPT will give results, outputs. So RAPT might say we need an additional 3 N20s. That means that we need 3 N20s every 1500 millimeters. And 1500 millimeters is a good place to start, particularly for the Australian code, because the maximum spacing you can have for your PT strands is 1500 millimeters. Anything more than that you need to justify by calculation. So let's start with 1500, and we will have one PT tendon in that 1500 millimeter design width, and we can adjust that to less than that, and that'll adjust our PT spacing automatically. I hope that makes sense. So if we had in 1200 here and we put in one PT tendon in this design, that would mean we would have one PT tendon every 1200 millimeters. If we have 1500 millimeters in here, that means whatever we have in here in the PT will be per 1500 millimeters. Okay, so now we put in our supports. Our columns are the same, but they are 90 degrees. Our beams are 350, 1500, and of course they are band beams. So band beams being where the depth is less than half the width. And the critical point here is that band beams in RAPT are treated as though they are flexural elements, so they are part of the slab. If you don't treat, if you select beam, RAPT will analyze the flexure up until the edge of the beam, and we'll take the rest as it'll take the curvature at that point and draw a straight line to the curvature of the next one, and assume that the curvature is linear. Whereas if we have a band beam, we're saying that we think that the stresses from the PT and in the concrete can spread into the beam such that flexure occurs in that band. If the beam is deep and sudden, then you can't get that dispersion of stresses to allow you to treat it as a flexural element. So it's a band. We'll put in our loading as before, and we will balance our loads at 0.8 of self-weight. Click OK, and RAPT has now given us a run to work with. So we will update our spanning members to 40 MPa. The slab and the beams will be poured together. Our bottom reinforcement cover and axis depth limits are fine. We know that the axis depth limit for PT must be that number plus 15 millimeters, but we will address that when we get to the pre-stress section here. So we go to spans. We have this is all correct, except these end spans, which are deeper, so we adjust those. Now we look at our columns, and we see that the columns are 100% stiffness. We want to be conservative and make sure all the bending moments are going into the slab, not into the column. So we adjust that. we don't have any drop panels. We have our transverse beams, and our load cases are as before. Now we look at our pre-stress, and in our pre-stress, I just noted something here. We have a band beam selected for these edge beams, but these ones need to be bands as well. So select those all as bands. Now we look at our pre-stress, and we can see that the profiles look pretty good. We must make sure our top cover is 25 millimeters so we don't get any popping. Bottom, I beg your pardon, 20 at the top, 25 on the bottom. Now, RAPT has designed this as 1.2 tendons, which isn't possible, so we round that down to 1. And we now go to allowable profiles, and under allowable profiles, these numbers here, which are covers, reflect what we have under here for cover. When we go to adopted profiles, we're looking at the center line of the strand, not the cover. And so when we look at this number here, which is our center line of the strand, or in other words, the axis distance, we know that our axis distance needs to be a minimum of 35 millimeters. So we add 35 millimeters, but RAPT says no, that is going to violate the cover limit that you have of 25 millimeters, because a cover of 25 millimeters plus the depth of the duct, or the distance from the face of the duct to the center of the strand, is more than 35 millimeters. So if we set to allowable cover, RAPT will calculate that axis distance to ensure that we meet this number here. So here we go. Down here you see the cover to the bottom of the tendon being 25 millimeters, which is equivalent to an axis distance of 40.1 millimeters. We can do the same thing here. And we are almost ready to look at the results. Go to output, and let's have a look at our deflections. So you can see that these panels in the middle here are really not deflecting at all, and we've got all the deflection on the end spans. So we really need to push the PT tendons up in these two middle spans. So we go back to input, and let's push these ones up to, let's say, 100. We can see what that does. Go to output, and we're having now about 20 millimeters on the sides and 5 millimeters there. If we look at our ultimate design, just to have a look at what that does, you can see that we still have a bit of room to move with our sagging capacity. So we might be able to change that to something like 105. And go to output, and yep, that's getting pretty much right. So now our deflections looking a bit better, 19.3. If you were worried about those, the next thing you could do is add haunches on your transverse beams. So if we add more detail here, we can add a haunch to either side. Okay, and we now have haunches. We go back to our output, and our deflections are improved further. Okay, now let's look at the reinforcement that RAPT has added. So we go to our graphics for Ultimate, and RAPT is adding a bit of reinforcement on the bottom here, because you can see that the initial bending moment capacity before RAPT has added any additional reinforcement is less than the minimum capacity, which is 120 kilonewton meters. So we need to add a bottom reo there, although you could argue what is the benefit of that reinforcement, because there is very little moment there. So why do we need to add such a lot of bottom reinforcement to give us ductility when it's not really needed? but that is a code requirement, and it would be up to you to decide whether or not you want to do that. Same on this side. And then in the center here, we can look at why RAPT is adding reinforcement. Here it's just to meet minimum reinforcement requirements. And at these points here, you can see we're just not quite. Oh, here it's because we are not meeting our serviceability requirements. And we can check that. I'll show you where we go there. Yeah, similar to this side here. So if we go to our service case, you can see that we have a limit here, which is our tensile limit in the concrete. Every time we exceed that, we need to ensure we add reinforcement to bring down those concrete tensile stresses to something that's more acceptable. That's in line with the code. So we can now go back to our input, and we can add reinforcement there. So we go to input, and we go to reinforcement. Oh, sorry, let's go to output. Look at the reinforcement that RAPT has suggested. And there's one other thing to note. So it's added the bottom reinforcement here, as we discussed. Here's the top reinforcement for serviceability, for cracking. And when RAPT, if we go back here, RAPT also says that there is a minimum requirement for RIO in these locations. That's this min top. That min top is a minimum quantity of reinforcement required for serviceability. It doesn't mean that we necessarily need to add that to our design. It's just telling us that there is a minimum amount required, and we need to check our code requirements there. For the Australian code, that's means that our bars must be centered no less than 300 millimeters apart. And so the minimum amount of reinforcement we'd need are N10s at 300 millimeters apart. That's what this 393 is, 393 millimeters squared. So we just need to ensure that whatever reinforcement we have at the top here is spaced no more than 300 millimeters apart. So let's add the reinforcement that RAPT has already added there into our design. We go to input, we go to user defined, and we click this button here, which is insert the design reinforcement pattern, which RAPT has already designed. And here you can see the reinforcement come in from RAPT. Now we can rationalize that. So let's start with the bottom reinforcement. We really only want a RIO bar that's right across this portion here. So let's get rid of the stuff right at the bottom. So I click that one there, and out that goes. Click that one there, out she goes. Okay, so this one we will make straight across from one side to the other. Now you can see that RAPT has required that we have 100% development, because it's assuming that basically that's the reinforcement, the developed reinforcement required at that point. So we will need to ensure that our reinforcement is developed all the way along that length from either side. So let's just make sure that our covers are correct, because at the moment it is on an angle. So we have 185 here and 20 there. So let's just improve this one. We're now straight, and we want to bring the left-hand side 50 millimeters away from the very edge to give us some cover. And we'll bring it in, let's say 1200. and we will know that we can't get 100% development, so we'll put in 50% because we can cog it on the left hand side, and we add 0 here because we will just have standard development length. Let's put in N12s, and we will have them spaced at 300 because we know that's the minimum spacing. Now if we just check this little bar here, we don't need. That's got rid of that little part there. And we need to do the same thing on the other side. So we can delete this one here. Delete that one there. And adjust these lengths here. Okay, 50% development, and these will be N12s at 300. And then let's see what RAPT thinks about that. So we can check, and actually it's not enough. So if we go to our design graphics, we can see that that is our initial, you see this orange line here, that's our initial bending moment capacity from the N12s at 300. Versus the required capacity. So again, we go back to our input. Let's change those to N16s. Check that again in our output. And RAPT is still adding a tiny bit of reinforcement there. Not by much though. Let's have a look at the graphical interface. So we might tighten up our spacing here to be, say, 250. Still required. Oh, still required, not having much luck here. Go back and check our ultimate design. Have a look where we're going wrong. So there it is. We are still coming back up there and not staying down below this line here. And so go back to our input. Let's make sure. I think we're not quite getting, we've gone 50 millimeters too shy. So this one should be 0 so that it comes right to this end here. Similarly with this end, that should be 0 there. And let's change those to N20s at 300. Okay. Still not quite there. So you can see that we're really having to add a lot of reinforcement to that zone there. And if I double it, hopefully, yeah, there we go. Now we're meeting the requirement. The only thing is we probably need to extend them a slightly bit more. So let's take them on both sides slightly further. And now I go to our output, and we should find that RAPT doesn't add any more reinforcement on the bottom. So it's just top reinforcement, which we had also added when we click this button here. So we go back to our top reinforcement, and we could probably rationalize that as well. We want these bars to be N10s at 300. And we want all those to be that. In fact, we probably don't need a bar right across there. So let's ensure that that is now less than that. here, I suspect we don't need. We'll delete that and we'll see if it's required. This bar here, again, our development on the right hand side can only be 50% if it's a cog. 50%, 50%. And we will have those at 10s at 300. Now there is another bar in there somewhere which I can't quite see. This one here, so let's delete that. There we go. Okay, we should do the same thing with this bar here to make sure we are symmetric. Don't get any confusion on site. So let's say that 50% development. And we will have it extending 1800 in. This one extends minus 275, so this should be 275. Oh, okay, now we're the same on either side. This middle bar we should center, so we'll make that minus 1800. And similarly, this bar here we should center. You can't really ensure that you're risking a mistake on site by leaving something like that. So we will have, and in fact we should probably keep these. $1800 either side so that we're consistent. This one we don't need. And we're pretty much there. So let's check what that does to our design. Let's see if RAPT still wants to add more reinforcement. You can see that all the reinforcement is in brackets, which is the user-defined reinforcement, and there is no need to add anything more. So if we now look at our deflections, deflections are looking pretty good. We should check our service. So in other words, our P on A, average pre-stress, and our average pre-stress is at about 2, getting up to 2.4. Now that might be slightly high, and we do have room to move in our deflections. We look at our deflections and we're at 17.5, so we could adjust that. And we could take down the pre-stress if we wanted to. We would then have to refiddle with the reinforcement to get that to work, and you may need to add some bottom reinforcement. So if we go to our ultimate, you can see we're fairly close to the limit here with our strength design, and if we take out a pre-stressed strand to reduce our P on A, then we're going to have problems with our bottom reinforcement and our bottom sagging capacity, and we don't want that. So you would either increase the depth of the section to make that 190 and 170, and then you could look at reducing the pre-stress, or leave it as is, as long as you don't have too much restraint in the system, which would be fine in what we're showing here, because we really don't have much stiffness in these columns in the weak bending direction. So now we go have a look at the other checks that RAPT has done. So RAPT will do a check on cracking and ensure that there is enough reinforcement. It will tell you what the spacing and bar sizes need to be to achieve your standard crack widths of 0.3 millimeters for RC and 0.2 for PT. For transfer pre-stress, it will check the compressive stresses at transfer and the tensile stresses in cracking. We've done our strength checks already. We do need to check our punching shear. So the slab itself has no problem with shear, as you'd expect, and punching shear also okay, as you can see in these results here. So we don't need to add any shear ties for punching. Our deflections, we have here 17.5 millimeters, the worst case. We need to add that to the beam design that we had done before. And our beam design was roughly, I think about 11 millimeters, but let's check. So we go back to our, and that was our beam design, 11.6 millimeters. Don't forget that we added a haunch to our transverse beam, which is the very beam we're looking at here. So we have to add that into this just to make sure we have like for like, and it'll only improve our results here. So let's make this 1900, and we've now got a haunch all the way along the beam. So if we go to output, look at our deflections, we are at 11 millimeters, and we need to add that to our slab deflections, which were 17.5. So we have a total of roughly 29 millimeters, and I'd suggest that that's fairly that's acceptable for total deflection. If you wanted to look at span on deflection, you would need to look at the diagonal between that point and that point, which is quite some distance. It's square root of 10.1 and 8.2, and you're probably looking at about 13 meters. So 13 divided by 250, or 13,000 divided by 250, gives you an allowable deflection if you are limiting your span to span on 250 of 52 millimeters. Now 52 millimeters is probably too much as a total deflection. You would always limit it to something less than that, and I think 30 millimeters is about right. So there's one last problem in this thing, which was the error that we had here, which is telling us we had a problem with our bottom axis distance. So we just fiddle with our pre-stressed axis distance, and let's just check what the distance was. It said it was at 5050 millimeters. So we can go to 5050 millimeters, and presto, it's at the bottom here. So let's just increase this to 45, and we should find that error disappears, and it has. So then the same, and now we have our answers. So that is how to design a slab from scratch. Of course, there are other solutions. There is a flat plate and a flat slab, and those solutions are provided in the RAPT examples in the RAPT directory. If you go to your directory on C drive under RAPT software and RAPT, and then there are a folder of examples. And just to give you an example of what that looks like, this is the folder on my computer, and these are the example files that are provided. I hope you enjoyed that, and please feel free to give us some feedback. Thank you.